This video comes right out of your textbook from page 178, number 6. 178 says, at least we'll start with part A, find three non-collinear vectors perpendicular to 2, -3, 1. So we want to find something perpendicular to, let's rewrite that vector just so we've got it in front of us, 2, -3, 1. So if you want to be perpendicular to that, well, that implies that we want to have two vectors such that their dot product equals 0. So let's call this vector, let's call it vector A. And let's let another vector, let's call it vector B, be represented by b1, b2, b3. That is, I'll have these two vectors, one I know, one I don't know. And by dot product, I know that vector A dot vector B has to equal 0. In other words, 2, -3, 1 dot product with b1, b2, b3 has to equal 0. Well, we know how dot product works. If you don't, I recommend watching the video on dot product. You just multiply each component correspondingly. So we get 2 times b1 minus 3 times b2 plus 1 times b3, which is just b3, equals 0. So now we have a formula, we have a pattern we can use to solve for the components that we need. Well, we need to get one of these components by itself. So for example, it'd be nice to get this b3 by itself. It has no coefficient, so I can move the other components over. For example, I'll subtract 2 times b1, and I get -3b2 plus b3 equals -2 times b1. And I can add on 3b2, add on 3b2, and I get b3 equals -2b1 plus 3b2. So now I have a formula for how to calculate the components. That is, I can use this formula and just come up with components for vectors that'll work. So for example, I could try, well, why don't we try b1 equals 1 and b2 equals 2. Well, if that's true, then b3 just equals -2 times 1 plus 3 times 2. -2 times 1 is -2, plus 3 times 2 is 6, so you get 4. So we've got one possibility. We've got a vector, so we have vector B equals, what was b1? 1, b2 is 2, and b3 was 4. We can keep going. The question actually says, find three non-collinear vectors perpendicular to this original vector, which I called A. So let's pick something else. We just want to make sure, non-collinear, so we don't want to pick multiples of the same numbers. So to avoid that, I'll keep choosing b1. That's something different than 2. How about b1 is -1, say, and b2, I don't have to change both of them, I just need to change one. I can leave b2 as 2. And then calculate b3 again. What's b3? Same thing as before. Use the formula -2 times -1 plus 3 times 2. And that equals, well, now it's negative times negative is a positive, so +2 plus 6 gives 8. And so we have a second possibility. And that second possibility is the b vector could equal, what did we pick? -1, 2, or 8. And really, there are a lot of possibilities, and I'll get to that in a moment. It's the second part of the question. So let's pick a different b1. We don't have to pick something smaller. We can be a little bigger, gutsy like 4. And let's pick a different b2. Don't have to, but we can. Let's pick -3. And so then b3 has to equal -2 times b1, which we chose as 4, plus 3 times b2, which is -3 in this case. And so we get -8 plus -9 is 17. So the third possibility, and these are in no particular order, I just chose numbers and then determined B3, and now I have 4, -3, and -17. I hope you can see there is an infinite amount of choices here, which leads us to the last part of the question, question B, how many vectors, in particular it says unit vectors, but that doesn't change our answer. How many vectors are there perpendicular to a given vector in 3 dimensions? And the answer is there are infinite choices. We could keep doing this process forever, and if you wanted to get a unit vector, you could just take any of these vectors, calculate its magnitude, and solve for its unit vector. So what did we do here? We found non-collinear vectors perpendicular to a 3D vector by using the dot product, creating unknown components, and then finding their equation, getting one of the components in terms of the two others, and then subbing in and solving for the third component. And we did that 3 times, but we could have gone on literally forever.